Right. And we are going. First off, welcome everyone to the Building AM, EOS, ANSYS, and PADT design competition for 3D printing. Before we get too far, I want to let you know that next week at the same time, we're going to have a really cool session, I think, about topology optimization by Jorge Pluma Reyes. He is an applications engineer at ANSYS, and he'll be showing you how to use topology optimization with ANSYS Discovery. Topology optimization is such a cool tool that I wish I knew how to use better. So hopefully you guys will enjoy that. All of these sessions as well will be recorded. They'll be posted on the competition webpage that you guys obviously have seen before. So the video recordings of these will be posted as well if you want to go back and review them for those that didn't make it to this session live. So why the competition? Why are we doing the competition? Building AM, a little bit of background about us. We are a not-for-profit organization based out of Utah. Our mission is to teach people about 3D printing, help introduce them to it, help them find networks within 3D printing, and get them used to using it. The competition kind of stemmed out of me and one of the other board members. One of the other board members is a professor at UVU. And I recently graduated with a degree in mechanical engineering a couple years back from BYU. And when I graduated, you sit down with the career counselor, they ask you, what kind of job do you want to have? And I wanted to do 3D printing. The challenge was that in the metal and industrial 3D printing world, I didn't have any experience. And so I applied with a bunch of OEMs. I really struggled. And eventually, I ended up landing this job at Optisys that I've loved. It's given me a lot of opportunities to learn about 3D printing. So the competition is our way of giving back to you, the students, and hopefully helping you to have a better job finding experience in 3D printing than we did. A couple pictures here on the slides. It's because 3D printing is a tool, right? And if you're like me, you've got a big toolbox at your house. If you don't know how to use a tool, it really doesn't do you any good. And so we're here to teach you about this tool. We want you to experience the tool through designing this drone. We want you to have experience designing for additive manufacturing and knowing the basics about additive manufacturing. So when you enter the workforce, you're already a leg up ahead of everyone else. I've included these CNC tools down here as well. And as we at Optisys can tell you, if you don't know a tool exists, you may be doing it the harder way or the wrong way, and you may be scrapping parts because of that. But if you know the right tool and you know how to use it, then you can do some really cool things. So that's kind of the point of the conversation or of the competition. So I want to walk through kind of how parts are manufactured, and you guys may be familiar with this already, but a brief overview. A lot of times in an ideal world, you will identify a customer need, you'll make a design, you'll manufacture it, and you'll deliver it to that customer. And if you know exactly what the customer wants, this is really nice because you can design exactly that, you can mass produce it, you can get it in their hands. One of the challenges, though, is what if customer needs have changed by the time you actually get to deliver it? Design and manufacturing is not a terribly fast process. It can take even years to do. And so if customer needs change in that time, then you're delivering a product that nobody wants anymore. The other challenge is what if someone else beats you to market? In industry, very rarely are ideas super original. And so if someone else beats you to market, then you just lost out on a lot of sales. So then we get to this other product cycle. In an ideal world, we could design, we could manufacture, we could deliver, and it will meet the customer needs. We can deliver the product that the customer wants when they want it. But the challenge here is it's a bit like guessing. You have to kind of guess what the customer is going to want months and even years down the road and manufacture it to meet that. And what if you guess wrong, right? Now you're stuck with lots of units that you can't sell because no one wants it. So what I would suggest is maybe the ideal product cycle is you design, you do small batch manufacturing, you deliver, you analyze whether or not you're actually meeting the customer needs, and then you do it all over again. And this is kind of where 3D printing really fits in. is you can go from design to manufacturing in as little as a day instead of months. And we've done that here at Optasys. We've taken designs that were just ideas at the beginning of the day, and we'll design it up, we'll do some review, and we'll do the actual 3D printing of it. And when we come in the next morning, we have product that we can pull off and we can sell. And so this allows you to be a lot more agile to what the customer needs. You're not investing in expensive molds for manufacturing. You can come up with an idea and you can get it to market fast so that you know if it's going to be successful or not. And then you can go back and make tweaks. And as you continue to mature and grow your product, then you can move to injection molding or die casting or one of the more traditional manufacturing methods. Why doesn't everyone use 3D printing? Garrett, you're making 3D printing sound super cool. Why doesn't everyone use it every time? Machines are really expensive, especially when you get into the metal world. Some of the bigger 3D printers, like the ones that we have here at Optasys, cost in the millions of dollars, multiples of millions of dollars. And if you go for some of the machines that have even more features, you're talking, 10 plus million to be able to run these machines. Some of these metal machines are so expensive that the companies that make them, they don't even sell them. They just sell the printing services because no one would be able to afford the machines. So they're really expensive. And part of the challenge with that is design and operation aren't really taught in school very often. Laser powder bed fusion, SLS, those are two of the, I would say, the less common technologies to be taught on in schools. And so when the workforce gets to the workplace, they don't really know how to use these big expensive machines. And sometimes we've seen that they can be really expensive paperweights. The other challenge with using 3D printing is that the cost per part doesn't tend to drop very much with quantity. When you're doing a process like injection molding, the more parts you print or make, rather, the lower your per part cost gets. You have a really high initial cost of making a mold, and then each part you make after that is really inexpensive. So the more parts you make, the lower the cost per part is. With 3D printing, you're investing in a really expensive machine, and you have to use that machine every single time. You can only fit so many parts on a build plate, and it can only print so fast. And so whether you print 100,000 parts or 100,000 parts, your cost per part pretty much stays the same. Now, you may be able to get some discounts on material. You may be able to get a discount on multiple machines, but even if you buy more machines, you still have the machine cost, the setup cost, the takedown cost. That's equal whether you're printing 1,000 or 100,000 parts. So those are a couple of the challenges. But what is it really good for? Initial product and small runs. I've got this picture of these pens down here. There's a company that I'm good friends with called Merit 3D. They specialize in reshoring parts that are typically made out of this country and customized parts that are mass manufacturable using additive manufacturing. And they're doing a job right now for a bank here in Utah that's celebrating their 150th anniversary. And they want these special pens to give out at their branches to be able to celebrate this 150th anniversary. And it isn't really practical for them to go invest in molds to make these pens just for this 1 year that they want to give those out. 3D printing is an amazing technology for that because it's completely customized to them, and they're really not printing all that many in the year. And so they don't have to make those expensive investments in molds and stuff. Customization is a huge thing as well. You can see on the pens that it's customized to this year. There are companies, I believe Gillette is 3D printing razor handles in the color that you want and the texture you want. There are shoes being 3D printed. Prosthetics are a big thing right now, being 3D printed that are customized to individuals' bodies. Consolidation is another wonderful thing. Part-to-part cost, 3D printing will almost always lose. But if you can take 30 parts and make them into one, well, now you're being cost competitive because now you're not paying for 30 parts and the connecting for it and the touch time to connect it. You're paying for one part that can be produced at once. And in the upper right here, you can see something that Optasys, this is something that Optasys finds really beneficial. We can take RF antennas that consist of many, many parts and shrink them down into one 3D printed part. And we service the aerospace and military industries. If you're shipping a satellite up into space, this is really, really valuable because each one of these connections would have bolts. And if you lose 1% of your bolts, well, now you're losing 10 bolts in your space flight. If you're printing one part that is connected to the rest of the satellite with 4 bolts, well, then the likelihood's really good that you're not going to lose anything on your way up into space. And so you're not going to scrap your $1 million satellite because of a loose bolt. And it's less expensive for them in the long run. The other thing is specialization. So another thing that Optasys is really good at is we service antennas that no one else can make across wide frequency bands in the RF space. And so we're able to specialize these antennas to cross these bands that no one else can do, that they would need 5 or 6 antennas to be able to meet. So what are SLS and LPBF? Like I said, these aren't covered very often in school. They're kind of rarer, but they are both powder bed processes. So basically 2D images are melted on top of previous layers using a laser. The powder bed is lowered, a new layer of powder is applied, the part is removed, it's depowdered, and it may undergo post-processing to improve desired characteristics. So here's a little diagram. Don't make fun of me, it's really lame. I think it explains it pretty well. Over here with the dog bone is our powder bed. And this is where our part is actually being made. You can see the light blue here is the powder that fills around the part, and the dark blue is the part itself. At the exposure plane up here at the top, the laser is coming out of our little black box, which describes the laser really well, and it's tracing out that 2D image. The build plate then drops down. Over here on the right, our powder feed bed is going to raise up a little bit, and our yellow recoder here is going to come across and wipe the powder across the new layer of the printer. And this is pretty similar between laser powder bed fusion and SLS. Here's a video I took of one of our printers actually printing. I could sit here and watch for hours the lasers actually running. You saw the recoder come across, laying the bed of powder. And then this particular machine has 4 lasers that are coming across and doing this 2D images of the part that's being produced. And once it finishes this, it's going to pull the recoder across again, and it's going to do it all over again. And it does this hundreds of thousands of times for a tall part over and over again. Essentially, it's a micro welding process. So what are the similarities between SLS and LPBF? Both use roughly the same size powder. So the powder that gets fed into our machines here at Optasys is roughly in the 20 to 60. SLS is a little bit bigger. It can be anywhere from 20 to 100 microns. But overall, really small powder. Both are limited in design by what you can get the powder out of. So we can print some really complex antennas, but one of the biggest challenges that we have here is getting the powder out of the antennas, because if we leave the powder in, then it doesn't work very well. Both of these processes produce end-use ready parts with minimal need for post-processing. So as soon as these parts come off the printer, you can do a little bit of post-processing and ready to ship out to the customer. The really cool thing, and where it kind of differs from like CNC machining, is that the used powder can be reused. So you can see here in the powder bed, a lot of it isn't part. So that powder that's not being used, we collect, we sieve out the really big pieces and the parts we don't want, and then we feed it back into the system and can reuse it on the next build. And because of the small particles we work with, sometimes because of the materials we work with, there's a lot of health and safety risks. Right before this meeting, actually, I was working on one of the printers, and it kind of looks like, if you guys have seen ET, the guys that have the big hoods and the jackets and the respirator tube going down, that's what I look like when I'm working on the machine. The aluminum is primarily what Optasys 3D prints in, and at this particle size, it can be explosive, catch fire really easily, and so it's a little bit of a challenge to work with sometimes. Let's see. Okay, So some of the differences between the processes. So SLS primarily uses a thermoplastic powder like nylon, and LPBF uses metal powders like aluminum or Inconel or something like that. For this particular design competition, you guys are invited to design either for nylon with the SLS process or aluminum with the laser powder bed fusion process. Supports are required for laser powder bed fusion, but often not for SLS prints. And that's a really big freedom that SLS offers. And the reason why is because laser powder bed fusion works with much higher laser powers. So the machines that we run here at Optisys, they're 400-watt lasers, and there's 4 of them in our big machine. And so temperatures get pretty high. In order to melt the metal, you obviously have to go much higher than you would to melt nylon. So I wanted to give you a couple of our other mentorship sessions. We'll go over things to be careful of when you're designing for 3D printing with these processes. But as an additive process engineer, I wanted to go over just kind of a couple of the gotchas that I had to learn as I took on this job. The first one is beware of sharp overhang corners. So if you're familiar with FDM 3D printing, you know that you can get away with up to a certain angle most of the time. And for laser powder bed fusion for SLS, that's very similar. One of the where you run into challenges though is with material shrinkage, especially with metals. And so up here you can see this sharp corner. This is bad because it's very thin, it's very sharp. And so when your material hardens after it's been welded, it's going to cause that to curl up. And that can rip out your recoater blade. It can crash your build, and it's expensive and painful, and it really hurts your soul. A better way is this bottom option down here. You can see that it's much thicker. It's gonna resist curling a lot more. There's a much wider angle on the corners and a much broader surface overall. And so just because your printer or your slicer says, hey, that's a really good angle, doesn't necessarily mean it's going to print really well. Large flat surfaces can really be a pain as well. And if you've worked with ABS and FDM 3D printing, you probably know this as well, that it tends to lift off the build plate. Well, metal parts and plastic parts tend to do the same thing. If you're printing a really flat, really large surface, then the forces cause it to curl up in what we call potato chip. So this is a business card I printed. In fact, I've got it right here. It's really thin. It's about typical business card size. And this was printed, and it even went through a heat treat process afterwards to relieve stress and hopefully allow it to stay straighter. And you can see where this arrow is. It actually curled up at that corner and did what we call potato chipping. It ripped the supports. And so if you look down in this bottom diagram, when the forces get too strong, it'll actually rip up that corner off the supports. And there are some things that we can do as process engineers or additive engineers to mitigate that. We can throw some really heavy supports, solid supports on there. But the challenge is you're probably still going to get some warping, and they're a pain in the butt to pull off, especially in metal, when you're pulling off these big metal supports. Beware of recoater walls. And what do I mean by recoater wall? So if you look at this equal sign over here that I'm printing on the left, when the recoater comes across, it's going to hit that flat surface straight on. And it's going to cause a big sudden force on your recoater. Sometimes that can cause your recoater to rip out. It can crash your build. It can be really bad. And so what some additive engineers call ice boxing is what we do. This equal sign on the right has been rotated about 7 degrees. And that, when the recoater comes across, it's going to hit that corner first, and it'll be a little force, and that force will gradually increase as it goes across the part. And that's a lot more gentle on our recoater. It's going to help our recoat layers be a little bit better as well. Beware of parts appearing out of nowhere. If you've worked with FDM, you know that parts need to be anchored somehow. And it can really sneak up on you. It seems like common sense, but I can't tell you how many times I've been preparing files for print, and I have someone review it, and they're like, this little part just appears out of nowhere. And so if you look at this M, you wouldn't necessarily think, upon initial look, that the upper left part of the M is lower than the right part. it kind of looks like a big overhang. But if you zoom in, that part is actually lower. So if you're printing this in a powder bed process or any 3D printing process really, and you try and make it appear out of nowhere, it's not going to work very well. It may lift, it may move, it'll look really ugly if it does work out. One of the challenges as well is how are your parts going to meet up together? If you look at these bottom examples here, these blue pointy things, there's a good and a better way to print it. The one on the left here, that may work just fine. We can put supports on the bottom, but our thermal expansion and contraction may make it so that that corner doesn't very much look like a corner anymore. It may look a little bit more rounded. It may have really rough surface finish. Maybe a better way to print it would be to flip it upside down and let it build up into it instead of trying to connect to it. And same way over here. With circles and big holes and stuff, you have to be careful because the angle may look really good for 3D printing over here at the side, but when you get up to the middle here, it's almost flat. And so sometimes we'll drop little supports here in the middle if we have to print in this orientation. Aware of abrupt changes in XY profiles. So most of the materials that I'm aware of, if you change cross sections really fast, you're going to get some weird material things happening. With 3D printing, especially in the XY profile, you're going to get some weird things. So on the right here is a part I just printed the other day. And you can see there's this big flat surface over here that immediately goes up into a thin fin. And you can kind of see this witness line across where that happens. And it's because the thickness is changing so much. And so it's shrinking different amounts. It's being pulled differently. So if we look over here at the left with this plus sign here, this would cause witness lines at the top and the bottom of the wide section. So maybe a better 3D printing method would be if we rotated it slightly and we added some fillets. And as you can see here, I dropped some orange lines to show that our thickness is almost consistent all the way across. And even when we do change thickness, it's happening very gradually. So we're going to avoid those witness lines. Fillets and stuff like that are free in 3D printing, so use them. And if you've ever been in like a CAD class or something, your CAD professor tells you like don't over fillet it. Throw that out the window for 3D printing. Fillets are free. Kind of a little bit of final inspiration for you. I stole this video from One Click Metal. They designed and 3D printed a aluminum drone that can hold about the same weight you guys are challenged to design for. So all So anyway, I thought that was really cool. They kind of did exactly what we're looking for you guys to do. Just in closing, we want this competition to be different. All of our sponsors, myself included, and several others outside of the organizations, we want to make you as successful as possible. So please, at any time, feel free to reach out to us by email. We'd love to connect you with mentors who can help you through this process. We know that it's new for you. We know that it's challenging, and that's a good thing because that's where we grow. We want you to leave this competition at the end of the year enabled with the 3D printing skills and knowledge you need to be a better student, but also to enter the workforce better and maybe come work with one of us. So anyway, thank you all for being here. I'm going to go ahead and pause the recording and then we'll open it up for questions.